It seems like it's pretty, like even the parking garage has been empty this morning, so I don't know, something's going on.
I think there's not a lot of students with Friday classes, or if they do have them, they're also available online. So they think it's not coming.
Yeah, because it's pretty nice weather, isn't it? The weather is keeping people away. It's like so really nice out today. I mean, it's cloudy but compared to what it was.
It was not really cold.
Yeah, and it's not like pouring rain. Yeah, I took a walk around the neighborhood the day before yesterday. It was warm, but it was like just misting. By the time I got home, like you could bring out my clothes. It's so bad. Anyway, so it's not like that. You know, it's good. Anyway, so this is slide 73 of the slide. So it's kind of like buried in the back. So the homework.
Professor,
Yes.
Professor, hate to interrupt. Do you think you could upload Wednesday's lecture? I just wanted to make a note of that before you get started.
There was a problem with it, and it didn't. Anyway, I'll get it up. But there was a problem. I didn't have the file, but I think I have the file.
Okay, thank you so much.
I uploaded it to this computer, but I didn't. But then when I got into Zoom, it said you didn't store this thing or something. So it should be stored. So I'll put it up when I get
Great,
it.
thank you.
Anyway, so let's see. Let me go over here for a second. So. Right, so we had this Kuhn model, which is the NL squared R squared. So and this is a kind of a Kuhn step and Kuhn unit. And then we also have the chemical, like the number of chemical monomers. So those are different. So you could write it in terms of that. And then we also said that this thing be like LLK, where L is N LK equals N chem L chem. In other words, capital L is the contour length of the chain. So you have this thing, and if you could straighten it out, so it would be pretty long if you could straighten it out. Right? In other words, if you have a 400,000 gram per mole polymer, and you stretch it out, it would be something like half a micron. So you can almost pick it up with tweezers. The hair is 50 micron diameter, so you couldn't really get it with tweezers, but it's anyway. So anyway, the actual object is going to be like 10 nanometers diameter, right? So it's actually super more compact. This thing's called the capital now. What happened?
Oh, it was a dog.
Oh, okay, sorry. I coughed at the same time. Anyway, so this thing has that size R squared, so 1/2 of the root mean squared size is going to be the size. All right, so that's like the Kuhn model, this chemical model, and then the other major model is called the worm-like chain model. Right, so that's like, so the Kuhn model has these steps, and it will freely jointed chain is the JC is the same thing as a Kuhn model. So you have these straight line steps, and then each step it can go in any direction, right? So it's freely jointed, meaning that the joint point between the steps can go in any place, right? And the actual polymer, it's got if it's a carbon, it's 109.5 degree angle, and then it can rotate about that. So it's much more constricted than it's freely joined on. Right? So you're going to have some modification of that. And we said that you can talk about a relationship, this C infinity, the ratio between the Kuhn length and the actual like chemical length of the thing. So that number is reflecting this kind of constraints to it. Anyway, the worm-like chain model is kind of more like a picture of DNA. Like you have this string thing like that, right? So you don't have any steps, and it's just like a continuous curvature, right? So you kind of need to talk about. So in this worm-like chain model, so if you're going to do a computer simulation of chains, and you want to determine what's the Kuhn length, and the computer simulation is going to generate something like that. Or if you have DNA, if you have a photograph of a molecule, or and also in scattering, you measure scattering, so you're doing like log intensity, log Q. So you have the Gaussian part where we have a two-dimensional part, and then it goes to one, -1. And that's called the persistence length. So the persistence length is just like, it's kind of an analogy to the mean free path of a gas. If you have a gas atom, and it's kind of moving around space, wherever it wants to go by KT, it's got a kind of an average length over which it goes in a straight line. It's like a step, but it isn't really a step. It's actually going where it wants to go. So it's not taking, right? So trying to get that thing, you take this chain and you talk about the tangent to it, this T hat thing, right? And from that you can get the persistence length. Right? So that's what this slide 73 is about. This worm-like chain model, right? So you have this squiggly thing, and you do a tangent to it. So you say like the tangent, if this path is R and it's going along kind of S would be the dimension along the contour length of it. And then dr, ds, R is a vector, gives you this tangent to it. It's like a unitless number. And so
Hello, Professor, can't hear you. Hello, Professor.
Would let me log in, and we have a quiz today. And I didn't know. Yeah, and you able to use your Google Sheets? I did it. I have to play for hours, but like.
I think I can hear now.
No, all right. Solve this somehow. Maybe I did it with my magic key here. Oh boy, now we get double me. Just. Is that from,
Oh, because they're testing right now.
there, all right, is it double me now? Can you guys hear still? All right, anyway, so.
Yes.
Yeah, we can hear you. Thank you.
Anyway, let me hide this again. Right, so this week's thing is this paper, and it's, so he's got paper, like Nanoscale's a good journal, and then he's got a paper in, this is the same guy, this Wang from Northwestern. So this is in PNAC, right? So this PNAS, Portuguese National Academy of Sciences. That's like a top journal. So it's like, it should be pretty high quality. You know, these two are both really good journals. Anyway, so anyway, it's difficult to get papers into these. So he puts a picture of himself in it. It's nice. There he is. And then what he's doing is he's got he's looking at what's called comb polymers, so like this. So this so where you run into this is like linear low density polyethylene, which is you polymerize ethylene units and you put in some butene or hexane units, and then you get basically the butene or hexene have an extra either methyl or ethyl group on the side, and however much you put in, so it's only the linear parts polyethylene will crystallize. So when you put those in, if you put them in at regular spacing, which you can do with a metallocene catalysis, which he also uses in here, then you can figure out exactly what the thickness of the crystal was, and the melting point of the crystal goes with the thickness. So the thinner ones melt faster than the thick ones. So you can pick your melting point for your polymer by putting in this metathesis polymerized kind of block copolymers of linear chains. So that's linear low density polyethylene. So it's a baggy, basically, kind of your baggy material. It's like a flexible, tough kind of plastic that you can blow films out of. Right. So anyway, so that's pretty big industry. The other kind of low density is just like a shotgun low density. So the original polyethylene is a free radical polymerization. They use liquid ethane at 50, I guess it's at 90 megapascals, or 900 atmospheres.
and giant reactors the size of like warehouses almost. They're like 6 stories high or something. And then they just put into this liquid ethane free radical initiators, and then just you have an explosion of this kind of branched structure out of it, right? So that's like total freestyle polymerization, like all kinds of branching and stuff. And that ends up being a pretty good material for, but it's kind of a junky plastic. You know, it's like your ultimate junky plastic. It doesn't have a lot of mechanical strength. Anyway, linear low density is an engineered polymer, right? So they're both low density, the low crystallinity. Anyway, he's looking at, for this kind of thing, there's a lot of simulation studies of this kind of molecule. Okay, and there isn't, and basically they look at like, if you have the chains on the side, it affects the persistence of the chains. And then people are looking at this, like you could put in target molecules like antigens on the surface of this, and you could use it for drug delivery to target cancer cells or immunosystem stuff, right? Basically cure most diseases or something like that. So there's a lot of different ways to make a stringy molecule that's got things hanging off. So he takes like 400,000 molecular weight acrylic polymers. This is like last week, we have an acrylic group and he's got some side groups. And then and he's going to stick these things onto it using a thing called metathesis polymerization. So metathesis. So anyway, so that's not what this is about, though. He's using this thing called single molecule localized microscopy to get the persistence length, right? So this is a Nature paper from 2021. So this is like basically take a molecule, long chain molecule, tag it with fluorescent groups, and then using the computer analysis, you can recreate nanos. So usually the wavelength of light is like 0.6 nanometer, so 0.6 micron, right? So it's like a micron. So you can't see things smaller than the wavelength usually. But because if you use fluorescence, the fluorescence on a molecular scale, somehow if you use computer analysis, you can generate nanoscale images using light microscopy. So that's, I guess, useful, you know, to do that. And this paper kind of tells how they do it. It isn't the same group. Then he published this thing in 2021 in this PNAS, which is another like Nature kind of journal, about using it to look at these brush polymers to get the persistence length of it, where there's already been a bunch of computer simulations of it. And he uses long enough chain, so you don't need to worry about the end group, like 400,000 is pretty decent length. And then he gets this tag thing, and he says from the tag thing, you can somehow generate this thing, right? So if you look at the question sheet here, there's an example of that. So, right, so this is where things get dicey quickly in this paper, okay? You don't find out until you look at the supplemental from the 2021, is that, so he tags his molecule, sticks it in the microscope, does fluorescence, gets this image. Okay, that's step one. Then he says, well, there's the blue and the yellow are identical. He picks by hand the yellow. Okay, and then he gets this image, which is what he published in the paper, in the PNAS paper. So it's like you can see, like, this squiggly thing is that yellow thing there, right? So he's thrown away all the blue arbitrarily, straight up, right? So, because if you measure the persistence length on this kind of triangle guy here, like, his process would kind of go haywire, right? Yeah.
You say persistence, are you talking about like
Yeah, he's going to take this, put it into a program, calculate the tangents of the bond, and then calculate this correlation function, the thing in the brackets that I had, tangent here, tangent there, dot product to get the cosine of the angle between them. And then he's going to sum that over all the bonds and get this CS as a function of the distance between the, S would be the distance between the 2 points in the chain. So you have a tangent at one point, tangent at another point, they're separated by S along the chain, along the contour. And then you dot product those to get the angle, the cosine of the angle between those 2 points. And you sum over all possible pairs at that distance S. So you start with 0, then that correlation would be 1 because the dot product cosine of 0 is 1. Then you go further out, and then the correlation is lost to some point. So you have an exponential decay in the correlation from that. Right, so he's going to take this image, handpick the yellow ones. Then he goes through a process of it's called thresholding, where you just get white and black on it, and feeds it into a computer program that does this tangent business. And then so these are kind of the enhanced images, and he's gonna get this is what he's gonna get, this persistence thing. So looking at this is totally bogus, like absolutely totally ridiculous. I mean, I hope you can understand that. Given this bar is like a micron, and these things are on a nanoscale. So I mean, absolutely, totally, this is bogus from the start. Okay, add to that, he takes the things, so he's going to take a solution of these things. Just an example of like totally bogus science. It's like a really high level journals. So like, he's going to put that and spin coat it 40 nanometer thickness. So and he's measuring at 250, which is like 4 or 5 times the thickness. We do that thickness in the for that'll be done. We have to have a long chain so that the image will affect the thickness. That's 22. So, and basically, you can't solve touch 22. You have to so anyway, so anyway, we were just talking about that because the plant Lyondell, I was out at Lyondell yesterday, and their plant in Italy is in the town. It's a town that they bomb in the Catch-22, but it's a nice town. It's got a castle and stuff. But anyway, so anyway, it is a Catch-22 for this guy. Like, he can't get around the fact that his things are bigger than the film that he's making, and it definitely 100% will affect the persistence if you squish your chains into a little thing, right? So obviously this came out in review in this paper, like I'd say half the paper is about why squishing it in doesn't matter. You know, it's a people argument today. Look at this thing. In terms of, all right, so what else is in here? Let me just get back to this thing. The original paper. The guy, so he uses the let's see, does he do that in this? There's 2 papers. There's like that one and that one, and this is the PNAS one, right? So I think this one he says maybe it's and this thing has a he's doing the same thing in both of them. This thing has a supporting information where most of the details are kind of hidden, right? So he shows the fitting of this thing here somewhere. that's his picture. That's what he gets after calculation. He calculates this correlation function. Oh, where is that? Then he gets equation 1 and 2. Here's his correlation function. That's the normal one that I showed you, like S over LP. That's not the one that he uses. He uses S over 2LP for this thing, because he says that that function, all right, so let me see where he does that. He shows the fits to that in here. Here, all right, so here he's got this, that's the correlation thing he spits out. So he says he's getting an exponential decay. First of all, like that's just, it isn't even really an exponential decay, it's just like a straight line almost, right? So anyway, so he says he's got the exponential decay in here. He's not fitting the hollow ones, he's fitting the solid ones. So he arbitrarily excludes some of the data and then just fits that middle part and gets this 250 nanometer. I mean, he has an argument for why he excludes the data. He says there's big errors, but he never bothers to calculate the error bars to show that, right? So it's like if there's big errors, you should show error bars. Anyway, so, and the low ones he doesn't use for another reason. So like a truncation error for the transform or something, like calculation. But anyway, so he gets that fit, he gets the persistence from that. So the fit, so where's the equation he's using? Here, this is the equation. Okay, so it's not the same equation. Okay, the equation is not LP. So that means that LP is coming out with. So LP, this was LP, LP, 500. Because LP is like larger than was really PNAS. Right, he gives a citation for that. Okay, so Polymer is a journal from Elsevier, and Polymers is a journal from MDPI, which is called a predatory journal, meaning that you pay to publish it and no one reviews it. And the cost to publish it is like $2,000, right? So you can publish anything you want. So it's not a reviewed journal. It's not legitimate, okay? And then this is his reference for the source of that 2LP thing, which is, it's right here, 2Ds, 2LP, 3Ds, just the regular one. And they give some kind of hand waving argument for why, actually, they don't even give an argument for why, and there's no reference to anything else. This is the source of that. So the source of that is some guy just said it in an unedited journal somewhere, right? And that's like the crux of the numbers, that the numbers he gets are reasonable. And they're not impacted by squishing the chains into this 40 nanometer mushy thing, right? So anyway, so that's bad too. And if he gives these references, but this is like the books, basically the books I gave you, and I looked at them and there's nothing about this in any of those books. And there's nothing about 2D, 3D persistence at all. So anyway, the one I didn't have that, there's a Grossberg book from Russia. It's a pretty good book. I actually got it. I might post it, but anyway, so that doesn't have it either. So even the one that was more arcane kind of doesn't have it either. So anyway, it's questionable. The whole thing is pretty questionable from the get-go. And then there's a lot of problems with it, but it does go through persistence. He does calculate that correlation function for micrographs. And then, so people do use micrographs to get persistence, you know, but they're a little bit, they use real atomic scale micrographs. Like you use, or if you're looking at DNA, you can see it. Like you can see the chain in optical with DNA. But if it's looking at actual molecules, use AFM to get it. So you have molecular scale resolution, and you can see, maybe you can get the persistence from that. And then otherwise you can get it from computer simulation or neutron light scattering, or you can get it from rheology. They can get it from that cutoff point in rheology. Anyway, so there's a few ways to get persistence, and this doesn't seem to really be one, you know. I mean, it's wishful that it could be one. So here, I mean, so he takes those films and he swells them with toluene. And he says it's kind of like a 3D swelling, but the film, if you have a film, And it's glued to the surface, like you can't, it's not gonna expand off. So he's got it on a silicon wafer. It's not gonna expand off the wafer, right? So there's only one direction of swelling for a film, right? So it isn't like, so you have your chains. So if you say you have your chains squiggling around there, then you're doing a 2G projection to get the persistence, which already should be like a lower number, because if you think about the persistence, so if you see a rod from a straight on, it doesn't have any, it's just like 0. And then if you look at its side, it's small, and if you look at straight, it's pretty large, right? So if you're looking at different projections of a linear segment, the length that you measure is different if you do a straight projection of it. So you could say like, I mean, I guess you could say like it goes in 3 directions. So if you only look at 2 of those directions, you get 2/3 of the persistence. Should get a smaller persistence when you see a projection of it, which explains kind of why, well, it doesn't explain anything actually, because he's measuring a larger persistence than so the projection thing would tell you it should be smaller. He's getting larger. He's getting 2 times as large. He's getting 500 instead of 250. So that means definitely the experimental thing is affecting the persistence. And then he does this thing. So when he swells it, he doesn't account for the fact that the thing's increasing in thickness by 20%, which means that you're going to get more of the more tilting off. So the thing should get smaller as it, I think, anyway, you can figure out for yourself what should happen when you swell it. But I think that in that picture of the taking projections of lines, that as the thing gets thicker and they become more random, you should get a smaller persistence, I guess. Right, so solvent swollen persistence is smaller by like 10%. There's the red ones are solvent swollen, the blue ones are just not solvent swollen, toluene. I think it's a smaller one. That kind of makes sense, just having a thicker film and doing a projection. He says it's because he solvent swells only the side chains, and when they solvent swell, they become more of a ball kind of, and then they force the chain to straighten out, and that makes it follow this other thing. So, and then he's got these power laws that he says he can't explain. And it says something about there's not enough size or length, molecular weight range here to get a real power law anyway. But he shows it nonetheless, and kind of seed in the waters for a simulation person to come along and say like that agrees. The simulations have been done on this already. Like pretty extensive simulations by good people have been done on these same systems. Not 400, but shorter chains, but still. I showed some in class, you know, and I'm not sure they come out with these 0.1 things, because he doesn't mention that. Anyway, so it's kind of a mess, but it does have to do with persistence, and did come out recently in a good journal, you know, so it's kind of worth looking at. But I think this is an example of that you could pretty easily trash this paper, and it's hard to believe that it got published, right? So he's got NSF is funding it, DMR, it's kind of hard to get money from them, and then all these foundations are funding this. So anyway, it's a little disappointing actually, but it shows you like, if you got all that money and then you have to justify it. So you wrote a proposal that you're going to use this fluorescence thing that you saw in the Nature paper to look at these brush things. That's 2021, this is 2023. And then, so yeah, that kind of makes sense. So the people say, oh, yeah, it sounds like a good idea. It should work. They say in Nature that you can get a molecular scaling of the things. You should be able to measure the persistence. And it has maybe could have some importance to something, even though I don't think there's any real application of brush polymers as far as I know. It's an active area study, and there's this business about biomedical application, but I haven't seen where anybody has used it for anything like engine oil or something like that, you know, where it would have like a market impact on something, but they do exist and people do look at this kind of issue. That's about it, I guess. Let's see, so let me go through the questions here. What else is here? This is just showing, oh yeah, he does show that these are the functions he had, and this is his fit to that exponential decay. I'm not sure what happened here. Anyway, this is inside the supporting information. This is that Nature paper. This is, all right. So this is the So there's another paper that came out recently on brushing. I just saw this when I was looking at brushes, so 2022, but it's using this raft polymerization we did last week. So just to show you that raft is kind of all over the place. The nice thing about raft is you don't have to have any kind of controlled conditions to do it. So you can literally do it in your bathtub. You know, it's like really, you can do it in water, you can do it in oxygen. So it's just like you can do this anywhere. It's really any idiot can do this reaction. It's like actually Neil Ayer's chemistry is not an idiot, but he uses a lot of raft to do growing like gels and stuff. So kind of similar things, you know. So basically everyone's using raft because it's so easy. Anyway, so you know, like it's much easier than some like anionic, cationic. And then, but he's using this metathesis polymerization, which is again like Nobel Prize, I think 2005. Two guys, the Caltech and the MIT guy won it. That's the paper. These are all. Anyway, so the questions here. So you might have a different opinion if you when you look at it. What else is blah, blah, and there's like explain the technique. So take a look at what he says, and then basically you tag the thing fluorescent. Prove when it's going to be like a spot, it's something really connected together. And it's kind of single molecule. I don't know. You could probably copy that picture and say this is how they do it if you want, but just so you can kind of see this. I guess you'll be seeing this more, maybe. It's hard to tell, or this could be just a one hit kind of thing. I mean, they show kind of how they enhance the thing with the different kind of resolution functions to look at the fluorescent tagging. Right, so anyway, you can, that's just a question about whatever you want to say. Like what I just did in the slide. All these techniques, like the light, neutrons got a light. They don't give. They don't give it. Let's see, it's this paper, right? They just give that equation right here. 3D, 2D. Like you can read it. Widely used, blah, 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 blah. It's convenient, da, 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 da. Or 3D, blah, blah, blah. Oh yeah, he says something like 3D accounts for 2 transverse directions. And contribute to decorrelate the tangent. All right, so that's what he says. It doesn't make any sense, okay? Like I don't, maybe you can, all right, you might be able to make sense of it. I think it's just like, ugh, like he's just like gone off the deep end. So these guys are in decent place, like I don't know, it's not bad places. So Korea has Seoul National University. That's the best place. And then Pohang University has a synchrotron. And then there's a lot of other universities in Korea. There's a lot of little universities. I don't know how good they are or what, but basically all the money goes to Seoul National and a little bit goes to Pohang in the south of the steel mill. There's like a huge, like all the US steel industry in the Vietnam War, like went to Korea, right? So that's why Youngstown and everything emptied out because Korea took it over. And Korea doesn't have any iron ore. So the US iron ore from Minnesota is shipped to Korea to make steel that's shipped back to the US. This is how world politics works, I guess. It has something to do with the Vietnam War. Somehow, something about parking nuclear aircraft carriers somewhere or something like that, you know? So anyway, so the steel company in Korea built a synchrotron, like as good as the Argonne National Lab synchrotron, like in Korea, and it was paid all for by a company that makes steel. And there's nothing really, you don't need a synchrotron to make steel. So they just had so much, so they had literally it's like $500 million, something like that, maybe 600 million. So they had that kind of pocket change to just say like, oh yeah, we need a synchrotron. You know, so I don't know. Probably, I don't think the US steel industry would do that for us, you know. At least you could say it went to good people, you know. I don't know. It's kind of funny. Anyway, so I'm not sure about this university in Korea. Like that's kind of a questionable thing. I don't know. This guy's at Purdue. They're in good places, yeah.
So, like, not taking into consideration like either of these papers,
Mhm.
what is the main difference between like 2D and 3D chain persistence? In your take, I guess.
I mean, it,
I'm not trying to.
well, you should be longer, right? I mean, you should have more persistence in 2D than 3D because there's a confinement effect. So, I mean, you could look at, I think you could do a macroscopic thing with this, like just take a string, you know, and like, so this, make the string into a ball and think about the, like what 60-degree turn would take in it, you know, and then put the string so it's completely laying on the table. And I think that you'll find that that distance would be larger on the table one. So actually it's physically larger. It's not a matter of the projection or something, you know, so he's saying it's 1/2 as big, like the LP would be half smaller on the table, which I don't see any possibility of that happening. There's no reason why it would be smaller persistence. The other thing is there's like interactions between the chain and the surface and stuff like that. Once you get to 40 nanometer, you can't ignore those surface effects. And also the stress field across that 40 nanometer film is incredible, right? It's totally free at the top and it's absolutely constrained at the bottom. It's stuck to it, you know? So I mean, there's a gradient of strain across that surface. It's like huge. And that's going to lead to like some kind of stretching of the stuff that's in it, I think, you know. I mean, you can figure it out. Probably this paper is written on it, but just using logic, it doesn't make. So his conclusion is it should be shorter by a half. But I mean, how do you argue that? Is there any maybe you can. I don't want to bias you, you know, but basically, I don't see any possibility at all that that could be true. I mean, so anyway, whatever. Maybe there's an argument for it, but I don't see it really. Anyway, let me finish these things here. So, you do a lot, but if you don't argue the other case, that's pretty good. You probably get a lot of points if you say it. I mean, I'm wrong all the time. If I reviewed this, it definitely would have rejected it. And the last name, yeah. And there's, it actually like, so probably almost anything you pick up can nitpick and find like, I mean, they talk about, who's the guy with the lead in genetics? And then, or they supposed to go with genetics, like they came back and statistically proved they didn't do that. It's like goes back a long time. Basically, everyone has an agenda. They have an idea. So they've made a hypothesis. They told a funding agency they can do this. Like they're inclined to just try to make it work, you know. And this is a case of a guy like totally hacking it. Like this is an absolute hack job. You know, so and the reason is like he's got to show a paper. He can't go back and say it didn't work. So it has to happen the Sloan Foundation and write another grant and say, but this will work, you know. It's like, well, you were bad, you know. Personally, like to throw good money after bad. Right, so, and then it's the thing about this. Way to prove it is kind of draw the cartoon. Then the cartoon will tell you what experiments you would need to do to show that. Like you could say like, there should be a density gradient. I can measure that with exfoliation. You can shoot an ion beam on and etch off and get the pieces from the film, things like that. So once you have a cartoon, you can say, what would I do to prove that cartoon? So the cartoon has to be accurate within what the information you have, and then you can use it to say, I'm going to do these experiments after. Like, that's the problem. Right? But having the cartoon stuff, there's no thing around that. You have to take like, whatever jumps going on, whatever your thoughts are, be able to draw it out, make sure that dimensions and things are right. And then you can say, well, what would I do to prove that cartoon? You can take the next step. Kind of closer to the truth. I mean, you never get the actual truth, be something good enough that you can kind of build a part from it that you need to do. I mean, you know, as long as you can, whatever you do, if it's good enough, it's good enough. Whatever reason that you use to get that function that you want to do. So at some point, it was right, you know, but basically, when it's important that we did this wrong. So that's about it. Shouldn't be too bad, hopefully. I mean, it could be bad. Maybe it's not too bad. This time I'm gonna. Yeah.
Did you just like yesterday, Dana Farber Institute, just had, I know a bunch of papers for also like data full time.
For what?
For data forgery and their.
Oh, really?
papers.
Okay, yeah. I mean, yeah, this isn't, yeah,
On that journal. It's Harvard's.
Yeah.
Cancer Institute.
yeah, I heard about that. But this isn't forgery. He's kind of making things up, but it's within the realm, like he can do that. It's up to the referees to say like, this shouldn't be published. And then when you pick up a paper, most of them are there's gonna be some extent of lies in every paper. There isn't one paper that doesn't have any lies in it, you know? So you have to be able to critically look at it and say like, I believe that. Like my logic tells me that that's true, or my logic tells me, so you can't just read the paper and take it as gospel. That's the thing. It's not the Bible. This is like actually just people in a real world situation, trying to get something out. So I don't know, but.
I have trouble finding one of our group members. This is them, and there's two different people with that name in the university, and I cannot figure out which one is which.
Oh, I had
Is
that
there a way to
figured out.
find that?
Yeah, yeah, let's see. That's, yeah. Yeah, it's definitely a good student, I don't know. Wait, yeah, she emailed me. Let's see. And I emailed he or her too, so I think I have email, I can find it, I can, CAO, right?
Yeah.
Chayako. I think that's the right one.
Is it with the I or
Yeah, with the I.
Okay,
CAOCI, I think.
gotcha.
Let me check again though, wait. What is it, CHI?
CHICA.
Yeah, Chayako with an I, yeah, just like, thank you, I said something. Chemical engineering major, oh, undergrad, chemical engineering, you should know her or he. So,
Nope, they must be on the other rotation.
okay. Well, now you know.
Yep.
All right, thank you. Bye.
Well, definitely something that's been a lot of this.
Um,
No, we're gonna you. Oh, yeah. You're doing this on the list.
Thanks, thanks.
No, they're just gonna be, it's just, they're gonna be telling me I'm not, but they,